Well, with that, I am going to get rolling. So like I said, any questions along the way, feel free. You will get a copy of all the slide material after the presentation is done. We usually do kind of an aftercare email to have a copy of all the slides, as well as, we typically put these up on YouTube afterwards. So there'll be a link. So if there was something particularly of interest or that you want a colleague to see, it'll be made available to them as well. So with that, I need it rolling. I'm Phil Harris. I'm the founder at Insight Analytical, and we're going to talk today about carbon capture with a pretty big focus on the application and then a bit about the analysis. So, sorry, multitasking, multi-screening here as I get messages. So I want to talk a little bit about Insight first. Although we represent and sell products, I don't think we act like your average distributor. At Insight Analytical, we like to position ourselves, if we can, in kind of a thought leadership type role. We like to look deeply into applications, understand why people need to do measurements. We have a very active customer training program between webinars and sample system courses. I'm going to talk a bit about a sample system course right at the very end of this. We make a real effort to understand our customer processes. We want to understand why they need to do measurements and then help them find the right analytical equipment to use. We have a fairly strong R&D focus in our organization where we're developing new products all the time. And we've launched a number of sample system products. As a rep or distributor, we don't carry very many product lines. We view ourselves as being experts in the things that we sell rather than generalists. We don't have a long line card because it's just too hard to know all those products and service them all well. We tend to focus almost entirely on spectroscopy-based analyzers. We don't carry it, probably one of the few reps that doesn't carry a GC line. We have a specific process that we like to refer to internally as the insightful approach to looking at applications, where we try to interact with the customer who comes to us, usually with a question mark up here. Let me see if I can get my pen working. Wrong way. Always tough going back to doing these because you lose all of your capabilities. So come in with a question mark. We like to interact with them, innovate, try to find alternative solutions to the question they're trying to solve, inform them of what might be good solutions. Where necessary, invent a new solution if needed to be, integrate that, implement it with them in the field, and hopefully they come out of it at the end with some new capabilities. And that's really our approach to the selling process, if you like. Okay, so enough about Insight there. I'm doing my little sales pitch at the beginning. So we're going to talk about carbon capture and storage, and really we're going to focus on 4 things. How do we get the carbon? So how do we do the carbon capture piece? Where do we put it? So primarily we're going to talk about geological sequestration because there's a large opportunity for that in most places, in Alberta here certainly. If we're going to go through that sequestration process, it's often different from going to happen in a different place than where we did the capture. So we have to consider, well, how will we get it over there? And so we're going to talk a bit about CO2 pipelines and what some of the concerns are we have with those. And one of those concerns is about the analytical chemistry side. And that's kind of where I like to usually play. And so we're going to talk about what do we want to measure there and how do we do those measurements. So when we look at carbon capture, it's interesting whenever governments come in with new regulations, and much of this carbon capture, of course, has come up as we started to talk about the path to zero, reducing CO2 emissions and all the things that have come up with the IPCC. Well, it creates whole new industries, and all those new industries create opportunities, and they also create problems sometimes. How do we do it? How do we do it safely and well? So when we look at carbon capture, we tend to sometimes view it as being four distinct industries, if you like. Post-combustion type industries, where we say we're going to try to capture this as a result, carbon CO2 that's been produced as a result of burning fuels. So we think of things like stat gas emissions. And this might predominantly be in things like power plants, but other applications, cement kilns as well. And then we talk about pre-combustion, which might be when we produce CO2 that was in with natural gas, for example, that came out of a reservoir, or that is produced as part of our refining and petrochemical processes, or in things like coal gasification applications. So we might be just trying to make hydrogen, steam methane reforming, and as a result, produce a bunch of CO2. One of the newer technologies that is out there is what's referred to as oxy-fuel combustion. And the idea there is if that you burn oxygen or burn hydrocarbons in pure oxygen, in theory, all you're going to produce is water vapor and carbon dioxide. And so if you condense out the water, you're left with pure carbon dioxide, which now you can put into a reservoir of some kind and sequester it, or if you can look at utilization, perhaps make some products out of it. And then one of the other ones that seems to get a lot of press is direct air capture, where people are actually trying to remove carbon dioxide directly from the air. And I have to thank the people at Amine Experts and SGS. Amine Experts specializes in sour gas and amine units. And amine is one of the common methods for capturing CO2. And they provided me some great information that I'll at least share one of the papers from them in the mail out after this. So when we look at methods for carbon capture, the technologies that are used to actually capture the carbon, by far the largest technology that gets used is amine absorption. We've had a long history with using amines to treat sour gases, things like H2S in natural gas processing and refining and petrochemical applications. We understand the technology really well. It's seen extensive use in refineries and natural gas processing, and now as part of the carbon capture approaches taken in power generation, we're also seeing amine get used there. It accounts for probably 75 to 85 or even 90% of the entire CO2 capture market is based on amine-based type capture. Monoethanol amine is probably the most commonly one used. It's been used since the 1950s for sour gas recovery. It's very cost effective, very available. If we want to, and especially when we start to look, say, in power plant type applications, if we want something that's somewhat more susceptible to or specific to carbon dioxide, we'll use amines like methyl diethanol amine, MDEA. It has advantages in that it's more selective to CO2, and MEA can be degraded by being exposed to high levels of CO2 for a long time. MDEA resists that CO2 degradation better. It is a more expensive product, and it's not as readily available, and that's why it's not as commonly used as MEA. If we further want to improve that amine process, we can add a chemical called piperazine, and it activates the MDA. It helps the MDA absorb CO2 faster and carry more CO2. So we are seeing units now coming out that you'll see people will refer to them as MDA piperazine units. There are other amines being tested, but again, these usually represent a fairly small part of the market. An alternative to MDA, alternative to amine, I should say. So amine is a chemical absorption process. The CO2 actually weakly bonds onto the amine. There's other solvents that we refer to as physical solvents. And Some common example of these are all usually patented solvents. I believe Selexol is, I believe, UOP. Cansol is Shell. Rectazole is, I believe, Linde. These sorts of solvents interact with CO2 in a slightly different way. The chemistry is different. They don't bond as strongly to the CO2, so they generally have lower regeneration costs. However, they can be expensive to get, but generally, I'm going to have a slide, or one of the slides coming up will mention that in general, these are one of the cheaper or more cost-effective methods for doing CO2 capture. The Shell Quest project here in Alberta uses Cansol. It's very suited to flue gas desulfurization applications, so it gets used a lot in power generation as well. The oxy-fuel methodology eliminates the need, if you like, to capture the CO2, to use a solvent like amine or Selexol. It burns the fuel, a hydrocarbon-based fuel, in pure oxygen. And the result of that, if there was no impurities in the fuel, would be just carbon dioxide and water vapor. And then if you just condense out the water, you're left with pure CO2 that can then be sequestered. Oxy-fuel represents a fairly small part of the carbon capture market right now, less than probably 5% of the entire carbon capture market. However, there's a company called Heidelberg Materials, and they're building facilities all over the world. They're doing one up by Edmonton that is using a physical solvent, but they're building one in Italy that is going to be an oxy-fuel facility. Produces just CO2 water, and water makes a purification much simpler. And then finally, there's a bunch of emerging technologies. Things like membrane separators, calcium looping, direct air capture, other ones. They represent, again, I say less than 5%, they're really probably less than 1%. I put some economics, a bit of economics information on here as well on this slide. So amine absorption, we can usually do for around $50 to $100 per ton of CO2 captured. Physical solvents run typically around $40 to $60 a ton. Oxy-fuel ends up costing us about $40 to $100 a ton. Most of that cost is in the oxygen enrichment. Things like direct air capture, current prices are around $250 to $600 a ton. If you look at the size of the facilities that are out there, the largest amine capture facility is the Gordon carbon dioxide capture facility, at least the ones that I know of. Gordon carbon dioxide in Australia is about 4 megatons a year. It's using MDEA. The largest physical solvent ones is the Great Plains Synfuel in North Dakota. It's around 3 million tons a year using Selexol. Oxy-fuel, there's not really many operating. The Calide Oxy-fuel project was, I think, in Australia or New Zealand, was around 75,000 tons. And for direct air capture, the largest operating direct air capture unit right now is in Iceland. It's the Orca facility, and it's 4,000 tons. So the largest amine unit is 1,000 times bigger than the largest operating direct air capture unit. So we have a number of different methods that we can capture the CO2. Now we have to think, well, once we do that, what are we going to do with it? And so what is commonly considered to be one of the predominant methods of getting this CO2 out of the environment is to do some sort of geological carbon sequestration, basically to put the CO2 back in the ground. And that's typically done in one of 4 different types of reservoirs. A common one is to use depleted oil and gas reservoirs. So if we've drilled for oil or drilled for natural gas, that hydrocarbon fluid was trapped underground. It was probably in a deep reservoir that had an impermeable rock above it that we refer to as a cap rock. The reservoirs are deep. And so because that reservoir spent tens or hundreds of millions of years holding trapped fluid inside of it, we know they're a good place to trap fluids. So if we can pump the CO2 down in there, we can fill that reservoir up with CO2. If that reservoir still contains oil, we can actually use this process to sequester the CO2, and adding the CO2 down in the reservoir pressurizes it and makes the oil flow better. So we can actually improve our oil recovery from an existing reservoir and capture CO2 at the same time. This, of course, helps with the economics of doing so. Another common way of capturing CO2, and one that is available usually in most parts of the world. So only certain parts of the world usually have depleted oil and gas reservoirs that they can put the CO2 into. But all over the world, there are lots of deep saline aquifers. And just like your soda stream machine, you can bubble CO2 into water and make carbonated water. Well, these deep saline aquifers, they're under high pressure, just like my soda stream machine. I put CO2 in under pressure, dissolves into the water. So I can pump my CO2 down into these saline aquifers and store the CO2 there. The saline piece really isn't necessarily a big part of the help, but we want to use saline aquifers because we don't want to do this into our freshwater sources. Another place that has been used for sequestering carbon has been deep coal bed methane seams. So if they know that there's coal down there, it's usually very porous. And if it's too deep to justify mining, we can then use that as a reservoir to put the CO2 in, and it'll fill up the pores in the coal. If there's methane, and there often is in coal beds, if there's methane there, pushing the CO2 down can help to displace some methane and produce more coal bed methane. Another one which has been proposed, which doesn't get used very often yet, is deep basalt formations. So basalt is a type of igneous rock that reacts with carbon dioxide and becomes a different mineral and permanently stores it under the ground. So we've got a number of different types of reservoirs we can put the CO2 into. The critical factors for a good reservoir is it has to be geologically stable. So we don't want something that's in the middle of a fault zone where suddenly there may be cracks to it and changes where it stores, how it stores the CO2. It's got to have sufficient porosity that we can put a lot of CO2 in there. Remember, this is really, if it's a coal bed seam or an underground gas reservoir, it's probably a sandstone or a shale. And so we've got to have enough porosity to be able to push the gas into all the holes. There's got to be a cap rock above it. By a cap rock, we mean a rock that's not permeable, that the CO2 can't move its way through. So there needs to be a porous layer and then an imporous and impermeable layer above it. And we want it deep enough so that we can keep the CO2 under high pressure, because that allows us to put more of CO2 down into that reservoir. Oh, I put this slide in. I forgot to take a slide out. This slide's in here twice. I'm going to use the next version of this. Sorry, I like this one a little bit better. Just like the graphic a bit better. In Alberta, we're in a really unique position in Alberta. We have a lot of natural gas. So there's a lot of deep oil and gas reservoirs that have been drilled already. And we understand their geology really, really well, because we've been doing a lot of drilling here. We have a really good idea of what the geology is like, whether it's stable, what the cap rock's like, what the porosity is like. We've got all that information. We've also got a lot of deep saline aquifers. These have all got stable cap rock up above them. And we've got a lot of CO2 production because we produce a lot of natural gas, because we produce a lot of oil, because we process a lot of those chemicals. We have a lot of carbon dioxide production. So we've got reservoirs that are in close proximity to industrial sources of CO2. And one thing I didn't mention when I talked about the different methods of capturing CO2, the capture is a lot easier if the CO2 is at high concentrations. So if I've got a natural gas that's got 10 or 20% CO2 in it, it's a lot easier to capture that CO2 than a stack that might only have a couple of percent of CO2, or direct air capture where there's only 400 ppm of CO2. So having sources of gas that has high concentration of CO2, which comes often from industrial sources, makes the CO2 capture easy. Also, if the industrial source is close to the reservoir, it means we don't have to try to pipeline the CO2 as far. So right now, Alberta Energy Regulator has approved 6 major CO2 projects. I've listed them there. I won't go through all the names. I will mention the Wolf Midstream one because we had a very active involvement in the analytical for that pipeline. One of the other ones are still in progress. Alberta Energy Regulator has put a second round of requests for proposals out for people who would like to make some carbon sequestration sites. And there are currently about 20 companies who put in proposals to build carbon sequestration sites all over Alberta and northeastern British Columbia. So we talked a little bit about the idea of that we can capture it. We've talked about where we want to put it, which is into these reservoirs. Now I'd like to talk a little bit about, well, how are we going to get it from where we captured it over to the reservoir? And so this becomes the CO2 pipeline piece. The captured CO2 is going to have to be transported to get over to where the reservoir is. This generally requires compression. We can squeeze more gas into a pipe if we put the gas under pressure. We can squeeze a lot more gas if we put the gas under high enough pressure that it gets over what is referred to as the critical point. So for all chemical species, whether it's nitrogen or carbon dioxide or methane, we can create what's called a phase diagram. And in that phase diagram, there will be a singular point that is referred to as the critical point. And if we're below the pressure of the critical point, we can be a gas or a liquid. Once we're above the pressure of the critical point, we form what is often referred to as a supercritical fluid. But in fact, it's only supercritical if it's above the pressure of the critical point and also above the temperature of the critical point. So for carbon dioxide, that happens at around 1070 psi and around 31 degrees Celsius. So if the gas is warmer than 31 degrees and the pressure is higher than 7.4 megapascals or 1070 pounds, it'll be a supercritical fluid. Supercritical fluids have some interesting properties for us. They can be very dense. as dense as the liquid, we can squeeze a lot of molecules into a small volume. Squeezing more molecules into a small volume means to move more molecules, we don't have to have as much volumetric flow in the pipe. We can use smaller pipes and get the same number of molecules per minute moving through them. The similar thing happens if we are below the temperature of the critical point. So if we're above the critical pressure, if our pressure is greater than 7.4 megapascals, but our temperature is less for CO2 than 31 degrees, we're in what's called the dense phase. So dense phase is similar to supercritical, but actually is even a little bit better. Dense phase tends to have lower viscosities, so it flows better. It doesn't have as much pressure drop as it moves along a pipe. When we're in dense phase or supercritical, the fluid's not as compressible. It behaves more like a liquid than a gas, which is beneficial for us because it lets us get to more stable flow rates. If we have a gas flowing down a pipe and we get pressure drop along the pipe, the gas starts to change volume, and actually the velocity of the gas changes. If we can keep it all in the dense phase or the supercritical phase, we can get very stable flow characteristics. So it means we would like to know for any CO2 pipeline, what pressures and temperatures do we have to stay around in order to keep that fluid in the dense phase? There's risks associated with dense phase or supercritical in that the stuff is very, very compressed. And so if we get a leak, it's going to spill out a lot of fluid. So generally, if we're going to run over really short distances, we'll transport CO2 as a gas. But if we want to run long distance pipelines, tens, hundreds of miles, we'll start to use either dense phase or supercritical phase transport. And so generally, our large pipelines are dense phase or supercritical. This would all be quite easy, or quite a bit easier, if the CO2 was always pure. It turns out that if there are impurities in the CO2, it changes its phase behavior. So the graph over here is just showing the phase diagram of different CO2 mixtures with different impurities in them. And what we end up finding out is that the critical pressures and temperatures change as we change the chemical composition. So if it's pure CO2, its critical pressure is 1,070 psi. As other components come in, the critical pressure can change, as can the critical temperature. So we want to have a good understanding of what other things are there in my CO2. Impurities in the CO2 are going to affect its critical points. It's going to cause it to change its density and its viscosity. And all of that is going to change how it's transported. That can also cause problems for us in our flow metering. And we have to remember that one of the big parts of the economics of carbon capture is that many governments have brought in tax benefits for how much CO2 you sequester and put to storage. So to know how much CO2 we're putting to storage, we need to know what our volumetric flow rate is, how many liters of gas we're putting in, and we also need to know how pure was that gas, or how much CO2 was in every liter of that gas. And so the changes in composition can affect our flow metering, and also that change in composition affects our CO2 purity. There's other issues that we have to be concerned about with impurities as well. I'm going to mention the bottom one first, corrosion. And so, whenever we have pipelines, and especially when we have chemical species that have some reactivity to them, and CO2 can certainly react with steels and can make carbonic acids, we have to concern ourselves with corrosion. But the contaminants that are there really affect how much corrosion we're going to see. If there's water vapor there, it can solvate other chemicals present in the pipeline, like the CO2, but also if there's contaminants like sulfur species or oxides of nitrogen, they can react with the water and make sulfuric acids or nitric acids that are going to attack the metal. So we have to be concerned about impurities present in the CO2 because those chemicals are going to potentially attack that steel pipeline. As well, there's other contaminants that can affect what goes on in the reservoir. So things like glycol, methanol, amine, these all come from the processing or the making the purified CO2, but the glycol can be used for dehydration. Methanol and amine can be used in the purification process. We want to make sure we're not losing those chemicals into the high pressure CO2. High pressure CO2, dense phase CO2, is an amazingly good solvent. Even if we were to say that, gas phase CO2 won't carry anything like compressor oils or glycols in it because it just can't dissolve into the gas. When we get into the dense phase, it becomes really good at dissolving these chemicals and carrying them along the pipeline. So we like to know if they're there because it means we're losing them out of our purification systems. Water is also a big concern because we mentioned it down here that it is a cause of our corrosion. And I found this really interesting paper. We're going to send a copy of it out. And it showed how soluble water is in carbon dioxide as we change the pressure. So normally, at constant temperature, and for this graph, we did this at 25 degrees C, we would think that as we go to higher and higher pressures, we can't dissolve as much water in it. So the curves go, we expect it to go like this. That at infinite pressure, we've got so many CO2 molecules, we have virtually no water molecules. And the curve moves like that for quite a while until we get up to around 1,070 psi. And the CO2 becomes supercritical there. And when it becomes supercritical, before it became supercritical, it could only carry about 1,000 ppm maximum of water vapor. As it becomes supercritical, suddenly it can carry 3,000 or 3,500 ppm. So water becomes much more soluble into this supercritical CO2. And that means that if we do get water carryover, or we have water in a pipeline someplace, this supercritical CO2 is going to readily pick it up. So this starts to give us an idea now of what some of the chemicals we would probably like to be able to measure in the CO2 are. It turns out that, these common contaminants, change phase behavior, cause corrosion, can affect upstream equipment and the reservoir. They can indicate that we have process operation issues. And the chemicals we're going to see there are dependent on the industry. So we picked a couple of examples of stream compositions that are shown in a couple of different papers. And typically we'll see CO2 concentrations more often in the 90 to 99% than that 75%. But the common contaminants that are there at the highest concentrations are usually nitrogen and oxygen. And I should have mentioned, oxygen's a problem too. Oxygen helps to make corrosion go faster. So we generally don't want to see oxygen in these streams. Argon's also there because it's difficult to separate from air in a lot of these processes. If we're doing this from some kind of combustion process, we are going to have argon there as well. But we do see things like SO2, NOx, H2S, hydrogen, methane, ammonia, and then water vapor in here. So these are some of the common contaminants we'd like to be able to analyze for, but it's industry dependent. So I tried to represent a number of different industries on this picture. So, this would be sort of like gas processing, natural gas, LNG. This might be ammonia or steam methane reforming, fermentation processes, refining, power gen, cement. Each of these industries, if we're doing carbon capture from those industries, there's likely going to be a different set of contaminants there that become critical measurements. For all of them, we usually want to know the CO2, the water vapor, and the oxygen. Those water vapor and oxygen, oxygen, when we think of rust, oxygen is iron oxide. So if we've got iron in our pipe and we've got oxygen there, we can make iron oxides. That happens more when the stream is wet, so we want to know the water. I show glycol down here because glycol's often been used in the dehydration to try to get the water out. So we might like to know if the glycol is carried over. In steam methane reforming, we're often worried about things like carbon monoxide, hydrogen, and then perhaps ammonia if we're making ammonia from the hydrogen. Fermentation, we can see alcohols come across. Refining and gas processing, more likely to see H2S, and maybe amines have been used to scrub the H2S. Cement and power gen from coal or from gas-fired or oil-fired, we're likely to see SO2 and NOx. So depending on the industry, there might be different contaminants that we say it's really important we measure these. We want to for sure measure the absolute purity of the CO2. This is our cash register along with flow. This tells us how much CO2 did I sequester? How much did I put away? And that's how big my tax credit is, my benefit, my cost benefit of capturing the CO2. All of these chemicals that could be present, even ones that don't necessarily cause corrosion, but things like nitrogen and argon, if they're diluting that CO2, they change the density, and that changes our flow meter calibrations. So to understand what our flow through the pipe is, we really would like to know all of the contaminants that are there, including things like nitrogen and argon. We want to know the moisture and the oxygen because it affects corrosion. And we want to know the SO2, the H2S, and the NOx because they affect corrosion. We'd like to know glycols and amines because they're indicative. If they're present in the pipeline, they probably came out from our processing unit that either purified the CO2, the amine, or dehydrated the water, the glycol. So we want to know, are those species, are those chemicals present in our pipeline? The other piece that makes this really interesting, though, is, normally when we think that we're putting chemicals in a pipe, we think that what goes in is what's going to come out. And there's been some very interesting studies done to look at what was fed into a CO2 pipeline at, let's say, a power generation facility, and what showed up at the sequestration reservoir. And so this graph shows the mass of certain chemicals in kilograms per year that went into the pipeline, kilograms per annum, and then different chemicals along the x-axis. So you can see that the most common chemicals going in are the argon, nitrogen, and oxygen. The most mass being moved to that pipeline that is not carbon dioxide is represented by the argon, nitrogen, and oxygen. That's really important because some people propose using infrared methods to monitor the purity of the pipeline, but argon, nitrogen, and oxygen are not infrared active. So we can't measure those using an infrared spectrometer. The other thing that's really interesting is if we look, for example, at H2S, we see that a lot of it goes into the pipeline and none comes out. So we have to ask ourselves, well, where did it go? What we see is there's a large coming out sulfuric acid. So sulfur species like sulfur trioxide and H2S, when they get into a pipeline that has moisture and oxygen there, they come out as sulfuric acid. So if we're measuring at the sequestration end of the pipeline, we want to be measuring for sulfuric acid. Similarly, we have NOx going in, but way less NOx coming out. Coming out, we see things like HNO2 and HNO3, acids of nitrogen. So it becomes important then, if we want to consider the corrosion impacts, that we perhaps don't monitor for SO3 or H2S, but we monitor for sulfuric acid. On the NOx side, it may be better to monitor for the nitric acids because that's what's going to cause the corrosion. So the question becomes, with all these chemical species, how am I going to monitor for it? And so now my sales cap is going to go on here for a minute, and I want to talk to you a little bit about mass spectrometers. Xrel is a process insights company. They have been making mass spectrometers now for 60 years. Very excited to work with them because I did my graduate work in the early 1980s on an Xrel mass spectrometer. So not only have they been working on them for 60 years, but off and on I have too. Well, 40. Mass spectrometers, I'm not going to talk too much about the principles of operation. They need a sample system in front of them, like most analyzers. We have to make sure the sample is vapor phase and non-condensing. Usually we like it to be well filtered. So this is going to mean that we're going to, and the pressure usually at the inlet to a mass spec is not very high. So we're going to have to put a sample system in place in front of our analyzers. We're going to want to do pressure control because we have this supercritical fluid. When we did a project like this, we put a lot of effort into thinking about how do I vaporize this supercritical dense phase fluid and make sure I do a good job of it. There's a bunch of tricks that have to be considered in there. The mass spec is particularly useful because it is fast, has a wide linear response, doesn't need any carrier gas, and it can do almost all of the measurements we need. It can do the inerts like nitrogen, hydrogen, argon, measure the oxygen, sulfurics, really can measure the sulfuric and nitric acids easily, SO2 as well and SO3, methane and H2S. It can measure things like methanol, ethanol, glycols, and amines. The only thing that you don't see on that list is water. And so we usually have to put a separate water vapor analyzer in. Give you an idea of what's in the mass spec, we have an inlet region where we let a very tiny flow rate of molecules come into the vacuum chamber. Those get into the ionization region. Now, what's called an electron impact ionizer. It turns the molecules that coming in from being neutrally charged to being positively charged. We have a set of ion lenses. Oh, I guess I can show that. We have a set of ion lenses right there that accelerate the positive ions and put them through the quadrupole mass filter. The mass filter separates all the particles out by, or all the molecules out by mass. And then we have detectors at the other end. Often two, one of the detectors is good up to measuring up to 100%, down to probably single digits or tens of ppm, and the other one can measure down into the ppb ranges. So what goes on in the ionizer region is that there's a filament there that is boiling off electrons. So it's creating this beam, if you like, of electrons that have high energy, usually 70 electron volts, and neutral molecules come in and go through the region where those electrons are. And when the electrons hit those neutral molecules, they knock another electron off and make positively charged ions. The positively charged ions are attracted towards a set of, people refer to them sometimes as ionizal lenses. Here's this referred to as a lens stack. They're accelerated to those to a known energy. That energy means for a certain mass, they'll have different velocities. So different mass ions will come out moving at different velocities. And when those go through there, they go into the quadrupole mass filter. The quadrupole mass filter is simply 4 steel rods with AC varying field on them that changes the electrical and magnetic fields that the molecules have to move through. If any of you did electrical engineering or physics, I remember right-hand rules that, if there's a magnetic field pointing in the direction of my finger, an electric field pointing in the direction of my thumb, there's a force on the particle to the direction of my other finger. And so by varying the magnetic fields, we can change which molecules can make its way through. So ions of many different masses come in, ions of a specific mass come out. I change the electromagnetic field and I can pick a different ion. In the interest of time, I'm going to skip the next slide. It just talks about maintenance on mass specs, but generally, I'll just say that mass spectrometers can be expected to run with relatively little maintenance, long-term operation, extremely stable, especially on clean streams like this. What we see from the mass spec, if we compare it to what we see from a chromatograph. So if we were to do chromatography and we had a mixture of nitrogen and oxygen, carbon monoxide, methane, we would have peaks that come out at different times. And we identify the chemicals in chromatography by when they come out of the column. And it might take 1, 2, 3, 5, 10 minutes for that to happen. Depending on the type of chemical, we might need to use a different type of detector. So if I wanted to detect trace sulfur species, I'd use a flame photometric detector. If I wanted to detect low concentrations of hydrocarbons, I'd probably use a flame ionization detector. If I wanted to detect something at high concentrations, I'd use a thermal conductivity detector. So constructing an application on a chromatograph can be hard because we have to pick the right columns, the right size injection volumes, the right carrier flow rates, and the right detectors. On a mass spectrometer, it is really a universal detector. A mass spectrometer can detect any molecule that can be put into the gas phase, and is linear over an extremely wide range. It can measure from parts per billions up to 100%. So if we put in a mixture of three molecules, let's say carbon dioxide, argon, and oxygen, we get a peak at mass 44 that corresponds to CO2. We get a peak at mass 40 that corresponds to argon. And we would get a peak at mass 32 that corresponds to oxygen. We would do all of that in the space of seconds. So mass spectrometers can give us information on every chemical that's present and do it all very quickly. So if we were to try to say, let's say, look at an application, here's one of the advantages of a mass spectrometer in this type of application over, let's say, a chromatograph. Suppose my stream was 99% CO2, 0.9% methane, and I had 5 parts per million of H2S, 5 parts per million of COS, and 5 ppm of benzene. The high concentration stuff on a GC I could do on the thermal conductivity detector. However, to do the 5 ppm of benzene, I would have to use a flame ionization detector. To do the 5 ppms of sulfur species, I would have to use a flame photometric detector. So I essentially have to build 3 different GC methods. One using a TCD, perhaps a certain size injection volume in columns. A second using an FID that might need its own injectors and columns. And a third using a flame photometric detector to do the sulfur species. If I wanted to do the same measurement on a mass spectrometer, I would just simply look at the parent ion peak for each of these chemicals. I would measure CO2 at mass 44, methane at mass 16, H2S at mass 34, COS at mass 60, and benzene at mass 78. I can measure all of the chemicals almost simultaneously within the space of a couple of seconds. So near real-time analysis, and with one device that doesn't have to be specifically configured. Not only that, if I wanted to add another chemical in afterwards, suppose someone came along and said, well, now I want you to measure toluene as well. I would just say, okay, what's the mass peak for toluene? I'll go look for that now. So one of the advantages of the mass spec is it's fast. The other is it's a universal detector in a single configuration. There's a couple of other ones that yet I'll touch on. If we want to do things like the trace moisture, moisture is difficult because it likes to stick to really clean surfaces, and mass specs are really clean inside. So moisture likes to stick to the walls of the mass spec. So it can be difficult to do trace moisture measurements. There is another Process Insights product from called Tiger Optics that works really well at doing trace moisture. So when we integrated a solution to do all of these measurements, we included a Tiger Optics as well as part of the measurement system. Be a little bit quick here at the end because I'm running out of time. I want to get you guys finished as close to one as I can. So why do we like the Xtrel Max 300 RTG for carbon capture applications? We can measure virtually all of the major components, from the glycols and the amines to the acid gases like nitric acid, sulfuric acid, H2S, oxygen, nitrogen, all of them on one device. It's got very fast response, so we can see transients and process variations. We can measure the inerts like nitrogen and argon, which say an FTIR can't. It's a single detector, unlike a gas chromatograph where we might need multiple detectors. It's easy to add new species if the specifications change. And we have to remember, this carbon capture industry is really quite new. I mean, it is only within the last decade that people have started talking about putting CO2 pipelines in and capturing lots of CO2 and having a tax benefit for doing so. It was used for enhanced oil recovery, but now we really want to measure purity and things like that. And so the specifications could change. And one of the beauties of a mass spec is we can add another component as needed. Photograph of a job we integrated for a CO2 pipeline. So X-Trail mass spec over here, Tiger Optics moisture analyzer. We also used a standalone, in this case, we used a standalone CO analyzer. It was a Teledyne CO. So that wraps me up on this subject. I got a couple more slides, and if anybody has to go, I do appreciate you for coming. A couple more slides. I'd just like to talk about some things that are coming up. We will be doing more of these webinars. We have 3 scheduled for this year, so 1 a month. On October 17th, we're going to talk about gas plant optimization, so things like measuring deethanizers, debutanizers, condensate stabilizers, how to improve the efficiency at your gas plant using process analytical chemistry. In November, we're going to talk about using infrared spectroscopy for crude oil blending. So things like measuring vapor pressure and viscosity using the infrared spectrum of crude oil, and how we can use that to improve the efficiency of our blending operation. In December, we're going to talk about some of the unique sample system components that we manufacture here at Inside Analytical. So those are our 3 main webinars. But what I hope is an exciting piece of news for some people. As I mentioned earlier, did I mention? Maybe I didn't. I used to travel the world teaching sample system courses. Usually these were 5-day courses at site. And so it meant people had to take 5 days away from the office to come and attend the course. And what I have decided to do is provide the similar sort of information as was in all those courses that I had done before with Tony, a different set of slides and different set of materials. But I'm going to give that entire program for free because it used to be $500 a day. We're going to do it for free. We're going to do it as a series of webinars. So I'll do 60 to 90 minutes per segment. There'll be about 16 segments to make up the course. We'll do a segment every 2 weeks. We'll leave some room for question and answers at the end. We'll provide some downloadable resources. We'll do it similar to how we've done it here as a Zoom and a LinkedIn Live. And not only are we going to do it in 16 sessions, we're actually going to do it in 48 sessions because I'm going to do it in 3 different time zones. So if you're in Asia Pacific, we'll do it, will be early in the evening for me. If you're in North America, we'll do it at lunchtime for me. And if you're in Europe, I'm going to do it first thing in the morning. So for Europe and Middle East. And so this is all going to start up in October, and we should have registration going on our website next week. Finally, I have a slide in that gives you an overview of the product lines that we carry. And I talked mainly about X-Trail and Tiger Optics. We do carry a number of other process insights brands like Total Sulfur Analyzers from Atom, the COSA Zentor Wobbe Index Analyzers, LAR for water quality, Alpha Omega for oxygen analysis, as well as other brands and analyzers we use in the hydrocarbon processing industry. That wraps me up. I have a last slide that's going to come out here. You will get a mail to follow with the full slide deck. You'll get a link to some technical papers. We have a carbon capture page on Inside Analytical. And I've given you the names of some of the people in the organization you can reach out to for more information. So that wraps me up there. Appreciate everybody coming. Tried to stay as close to being on time, so keep it as an hour. I think I did pretty well. So thanks again, everybody.